Hello there and welcome! Today we're going to be taking a look at one of the real cornerstones of computer science. It's a wonderfully elegant solution to a problem we all face in one way or another. We're talking about Dijkstra's algorithm. So let's dive right in.
Have you ever stopped to think about how your GPS or your phone's navigation app does what it does? I mean, how does it almost instantly figure out the absolute fastest way to get you somewhere, sorting through potentially millions of different routes? Well, you might be surprised to learn that the secret sauce behind that is often the very algorithm we're discussing today. So, what is it, officially? Well, it's what we call a greedy algorithm. Now, don't let the name fool you. Greedy here doesn't mean selfish. It just means the algorithm is incredibly focused. It always makes the choice that looks best at that particular moment. The underlying idea is that a series of these best local choices will eventually add up to the best overall solution. Its main job is to find the shortest path from a single starting point, or node, to every other node in a network or graph.
Right, probably the easiest way to get your head around this is to think of it like exploring a map. Imagine you're standing in your hometown with a blank map. Your goal is to find the shortest possible route to every other town. The simple rule you're going to follow is this: always expand your map by traveling to the nearest town you haven't fully explored yet. That's the core idea.
And here are the specific rules of the road for our little expedition. First, you've got to set up your map. The town you're starting in? Well, the distance to get there is 0, naturally. But every other town? For now, we'll say they're infinitely far away, since we don't know a path yet. Then, you just repeat a simple process. Pick the unvisited town with the shortest known distance. From there, look at its neighbors and ask, is it shorter to get to you by going through my current town? If the answer is yes, you update your map with that new, better route. Then, you mark the current town as visited and you do it all over again.
All right, that's enough theory. The best way to learn this is to actually do it. So let's embark on our first journey together. We'll use a very simple map with just 4 towns to see exactly how this process unfolds.
Here's what our logbook looks like at the very beginning. We're starting at town A, so the distance to itself is, of course, 0. As for towns B, C, and D, we haven't found a path to any of them yet, so for all intents and purposes, their distances are infinity.
So, where do we start? Well, our first move is pretty straightforward, isn't it? The node with the smallest known distance is our starting point, A, with its distance of 0. So that's our first choice. We visit A and start looking at the roads leading out of it.
Okay, from A, we can see 2 direct paths, one to B that costs 4 units, and one to C that costs 2. So we update our table. The distance to B is now 4, and the distance to C is 2. Notice D is still unreachable from A, so it stays at infinity. And crucially, we now mark A as visited. We're done with it. We won't be checking it again.
Right. What's next? We need to make our next greedy choice. We look at our unvisited towns. B is at a distance of 4, and C is at a distance of 2. Well, 2 is obviously smaller than 4, so our algorithm greedily chooses to visit town C next. Let's see what we can find from there.
Now, standing at C, they look around at its unvisited neighbors, and aha, there's a path to D that costs just 1 unit. So, what's the total distance to get to D through C? It's the distance to get to C, which is 2, plus this new leg of the journey, which is 1, that gives us a new total of 3. And since 3 is a lot better than infinity, you bet we're going to update our table for D. And with that, we're done with C, so we'll mark it as visited.
And after we continue this process for the remaining towns, we arrive at our final result. This is the beauty of it. The shortest path to B is the direct one, costing 4. The shortest path to C is also direct, costing 2. But the shortest path to D isn't direct. It's actually faster to go via C, for a total cost of 3. The algorithm found it perfectly.
Okay, that first one was a nice warm-up. But the real magic of Dijkstra's algorithm shines when the most obvious path isn't actually the best one. Let's tackle a slightly trickier map to see this in action.
To save a bit of time, let's jump ahead a couple of steps. Imagine we've already started our journey on this new map. We visited our starting point A, and then we visited C. This table shows the current state of our knowledge. Right now, the shortest path we know to B costs 7, to D costs 11, and to E costs 5.
So according to our rules, we look for the smallest unvisited distance. That would be E, with a distance of 5. So we go there, but it turns out to be a bit of a dead end. No shortcuts from E. So we look at our list again. The next smallest unvisited node is B, with a cost of 7. So let's visit B. And this is where things get interesting. Pay close attention to what happens now.
And this is the aha moment. Look at the entry for node D. Before we visited B, the best path we knew had a cost of 11. But from B, we've just discovered a path to D that only costs 2. So the new total path is the cost to get to B, which was 7, plus the cost from B to D, which is 2. That gives us a new, much shorter distance of 9. We've just found a better route. That right there is the real power of the algorithm in action.
Brilliant. So we've seen how it works. But now, let's pop the bonnet, shall we? Let's take a look under the hood at how efficient this method really is, and just as importantly, where it falls short.
The efficiency of this algorithm really hinges on that one crucial step, finding the unvisited node with the smallest distance. If you do it the brute force way and just scan a whole list every single time, your workload grows quite quickly, what we call OV squared. But we can be much, much cleverer. By using a special data structure called a priority queue, which you can think of as a self-sorting list that always keeps the smallest item right at the top, we can find that minimum value almost instantly. This is a game changer, improving performance dramatically to OE log V. For any large map, that is significantly faster.
And what about how much memory it uses? Well, it's actually quite lean. You really only need to store the map itself. That is, all the towns, or vertices, V, and all the roads, or edges, E. So the space it takes up grows in direct proportion to the size of the map. Pretty efficient.
But the algorithm is not without its flaws. It has an Achilles heel, and that is negative edge weights. It simply cannot handle them. Why is that? Well, the entire logic is built on one core assumption. Once we visited a node, we found the absolute shortest path to it, and we never have to look back. But imagine a road that paid you to travel on it, a negative cost. Suddenly, you could find a very long looping path that ends up being shorter just because of that negative value. It breaks the fundamental greedy logic of the algorithm.
So, given its power, but also this one major limitation, how do we know when Dijkstra is actually the right tool for the job? Think of this table as your cheat sheet, honestly. This is what you'll want to remember. For finding the shortest path from a single point, where all the costs are positive, like road distances in a GPS, Dijkstra's is your champion. It's fast and reliable. But the moment you have a problem with potential negative values, you'll need to reach for a more robust tool, like the Bellman-Ford algorithm. And if your problem is different entirely, say you need to find the shortest path between every single pair of towns, then you'd use an algorithm like Floyd-Warsaw. It's all about using the right tool for the right job. So, if you take just one thing away from our discussion today, let it be this. The crucial point is that Dijkstra's is about systematically expanding the closest node until all shortest paths are found. It's that simple, methodical exploration from the nearest frontier that guarantees the correct answer as long as you're playing by the no negative weights rule. And that leaves us with a final thought, doesn't it? This idea of making the best local choice, the greedy approach, is incredibly powerful. It makes me wonder, what other complex, seemingly unsolvable problems, maybe even outside of computing, could be simplified if we just focused on making the simplest, most obvious next choice? Something to ponder.